Okay guys, so we're going to continue talking about topic 4 here. The last video left off on example 7, so we're going to go ahead and jump right into solving example 8. So in example 8, we're dealing with a 3D system, and our goal here is to determine the moment MAB that is produced by the force, which is the 300 Newton force pulling down at point C, which tends to rotate the rod about the AB axis. And the AB axis is part of that pipe system as shown here. So the first thing we're going to do here is, I've kind of mentioned this before, but whenever we have a 3D system, I prefer to do vector analysis. Let's see, my Apple Pencil is deciding not to write right now. Oh, well that's fine. It's not charged. Okay, so you guys can go ahead and fast forward this part. Maybe I'll just talk for a little bit while that gets some juice in it. But basically, whenever we have a 3D system, we are going to tend to use vector notation here, or vector analysis, rather than trying to find the moment arm or the perpendicular distance from F to AB, because that's going to be a much more difficult task than just going right ahead and doing the cross product of R cross F, and then multiplying that by UB, or the unit vector in the B direction. So if you guys remember the definition of UB, or the unit vector in the B direction, it basically defines the direction of the AB axis. So because that rod does not lie on the X, Y, or Z plane directly, it's along its own axis, we need to define that direction using the unit vector at B. Okay, let's see how much we have now. So, okay. MAB is equal to the unit vector at B multiplied by the cross product of R and F. Okay. And again, this unit vector defines the direction of AB axis, which we don't know. So we're going to start with that actually. We're going to start with the unit vector in the B direction. That's just equal to the position vector to B divided by the magnitude of that position vector. So here, to get to point B, we need to travel 0.4 on the X, or 0.4 along the I, and a positive 0.2 along the J. And then we're going to divide that by the magnitude, which would just be the 0.4 squared, plus the 0.2 squared, and we end up getting 0.8944 in the I, plus 0.4472 in the J. And this vector R is directed from any point on the AB axis to any point on the line of action of the force. Remember, that's very important. So remember, this unit vector here, or the vector R, this position vector, is directed from any point on that AB axis to any point on the line of action of the force. It does not have to be that perpendicular distance. Okay, and I'm going to give you guys some examples of that. So what I mean by that, let's look at the position vectors RC and RD, for example, down here. Okay, so here is the force, the line of action of the force, and this RC position here is a possibility that we can use. It's directed anywhere from, of course, the AB axis, so this is point A, to the line of action, that's correct, but we could also use RD. This is another option. We could also use any other R vector that acts along that area. So it can be R from B to C can also be used. R from B to D can also be used. These are all possibilities that can be used. Of course, you're going to want to select the most easily identifiable vector to put in. So for simplicity, I'm going to choose RD here. It acts directly along the x-axis. So all I have to deal with is 0.6i, and this is measured in meters. And my force, of course, the force vector, is negative 300 in the k direction. This is in newtons. And I pretty much have everything I need now. So my MAB, the vector in the AB direction, is the unit vector at B dot R of D cross F And if I want to plug everything in now, I'm going to start with this cross product here, 0.8944, 0.4472, 0.6, 0, negative 300. And remember, when I want the moment about a different axis, I'm no longer going to put IJK here. I'm going to put here, this is all now the unit vector instead of IJK, because I don't want it in the I, J, or K direction. I want it in the direction of that unit vector at B. So if I want to solve for all this, whoops. Zero times 0. And then we're going to add 0, 0.6 times 0 minus 0 times 0. I'm just basically solving for the determinant here, or just plugging in that vector formulation that I had put for you guys on the previous slides. Okay, and this is the answer. So because this is positive, that means that MAB, since it's positive, MAB acts in the same direction of the unit vector. Okay. Now, if I wanted to write MAB as a Cartesian vector, I can really easily do so by just taking the magnitude 80.5 and multiplying it by the unit vector, because that's in the same direction as MAB. And I end up getting 72 in the I. Why I put the dot there? Just 72 in the I, plus 36 in the J, and that's in Newton meters. Okay, that is it. Now, if AB is defined using the unit vector from B to A, I want to tell you guys, you're going to get the same answer. So what if I use the unit vector going from B to A? That's okay. I'm basically going to get MAB is going to be negative 80.5, but that's okay because that just means it acts opposite to direction of BA, which is true because we know it acts in the direction of AB. So we get the same result either way. Okay. All right, so the next really important concept that we're going to go over is a couple moment. So I want you guys to think of having both of your hands on the steering wheel. Okay, I know that you guys, we can get away with driving with one hand, but that's just because of the ease of the steering wheel. But imagine you have two forces on a steering wheel. Actually, I have a picture here. I just realized that. And you're pushing up with this force here, this hand. You're pushing up with one hand. Kind of highlight this in red. It's kind of hard to see here, but this is one hand pushing up, and you're kind of pulling down with the other hand. And I'm sure you guys have noticed this when you're driving your car, but this creates a rotation. Okay, we call these kind of equal and opposite forces a couple. Okay, and this couple is a type of moment because it causes rotation. Okay, and between the couple, there acts another really important concept right here, which is the moment arm, this distance D. Okay, and because both of those forces are important, the resultant of the couple equals 0 because they're equal and opposite. Okay, so the couple does not produce any translational motion or resistance. The only outcome of it is either rotation, or in a static system, it produces a tendency for rotation in a certain direction. You can think of that like something blocking the rotation, but it would be trying to rotate. Okay. How do we define the moment of a couple? It's pretty much exactly the same as before. M equals FD. But in this sense, we're never going to add the forces. You just take the direct magnitude of the force. So if you have a couple going in this direction, that's 20. A couple going in this direction, that's 20. And we have a moment arm between them. That is 5 feet, let's say. It's pretty big, let's say 5 inches. Then we would have moment is equal to 20 times 5 inches, and that's pretty much it. Okay, you're only going to take one of those forces because those forces act in conjunction with each other. Okay, determine the direction of the moment, we use the right-hand rule to determine that. Just like we had previously used the right-hand rule, same right-hand rule is going to be used here to determine the direction that that couple is acting in. Okay, and of course we have the same function for, or the same vector formulation that we had previously for moments. It's still going to be r cross f, and the resultant couple is the vector sum of all couple moments on the system, just like before. Okay, so let's put this all into an example. We're going to go ahead and do example 9 here. So what we want to do here is we want to determine the resultant couple moment of the 3 couples acting on the plate. The 3 couples acting on the plate. So the first thing we want to do is we want to identify all of the couples. So I'm going to draw them each in a different color. So they're already labeled here, and I want to make it very clear. This F1 here and this F1, they are not 2 separate forces. That's why they're both called F1. They're the same force acting in conjunction with each other to cause rotation. And that's why we don't count them twice. So F2, same thing here. That's why they're both 450. And F3, these parallel forces that cause rotation is always, it's at 300 there. So we have 3 sets of couple moments here, and we want to determine the resultant, which is just equal to the sum of all moments. I'm going to assume counterclockwise is positive, and my resultant moment is equal to, let's take F1. F1 is going to produce a clockwise rotation, so it's going to be negative because counterclockwise is positive, times the moment arm. F2 will cause counterclockwise rotation, so I'm going to add it. And F3 is going to cause clockwise rotation, so I'm going to subtract it. Now all I have to do is plug in everything. It acts at a moment arm it's giving to us of 4 feet. And then I'm going to add the 450 times a moment arm of 3 feet. And then I'm going to subtract the 300 times a moment arm of 5 feet. And I get an answer of negative 950 pound-feet, which just means 950 pound-feet clockwise. Very straightforward. Okay. Let's go ahead and try another example here. I'm actually going to do this example I'm going to provide 2 solutions for this. So I'm going to do a vector analysis and a scalar analysis to show you guys that you can use either of these. So let's start with solution 1, which is a vector analysis here. Solution number 1, vector analysis. Okay, so my moment here is defined by, I should probably read the problem. So we want to determine the couple moment acting on the pipe shown, and segment AB is directed 30 degrees below the XY plane. So here, my moment is equal to the position vector to A cross the force, which would just be negative 25 because it's acting down in the K direction. And then I have one more force, right? Or the total couple. I need to measure the distance that it takes me to B multiplied by the same force, right? But now if I'm going into the direction of B, I'm going to have 25K going up. So I know this is a little bit different than the scalar analysis where we consider it to be one system causing rotation. We still have one system causing rotation here, which is that 25-pound force, but instead of having to get that moment arm distance between them, we're going to separately kind of consider each one of these from our starting point because we have two R's here. So we have the RA and we have the RB. So we need to count for RA and RB separately. And that's why we kind of split it up like this. You're going to get the same answer either way. So you can do the scalar analysis or the vector analysis, but I'm just going to show you both. So here, RA is just 8 in the J direction, cross the negative 25K force, and then we're going to add, we have this 6 cosine 30 in the I, plus 8 in the J, minus 6 sine 30 in the K, and then cross a positive 25K. And if I multiply everything out, I end up getting 200 in the I, minus 129.9 in the J, plus 200 in the K. And I get a total, actually, I'm sorry, I get 200 in the I here. These cancel out here. And I end up getting a final answer of negative, I'm going to say approximately 130 in the J, and this is in pound inches. Okay, so I'm going to highlight this answer. It's pretty much easier to take the moment of the couple forces about a point lying on the line of action of one of the forces. So that's another option that you have as well. Okay, so for example, let's say I picked point A. Okay, I'm going to show you another way. This is kind of a third solution. But let's say instead of having to do these two separate analyses, I wanted to say my moment is equal to RAB cross the 25K, producing that rotation on the system. So I would say my RAB is actually 6 cosine 30 in the I minus 6 sine 30 in the J. So that's the direction from A to B, cross 25K, and I end up getting the negative 130 in the J, pound inches. So I still get the same answer. That's another option there. That's still with vector analysis. Okay. The third solution I want to show you guys is scalar analysis. Okay. And even though the problem is 3D, it's pretty simply set up to where I can still use M equals FD here because I can see really clearly that my D, the distance between these two, I should probably use a different color here. The distance, this parallel distance between the couple, you see how this here is 6. That means that this is just going to be 6 cosine 30. That's going to be my D. So it's pretty easy to recognize that, and you can go ahead and say M is equal to 25. This is equal to 5.196 is equal to 130 pound inches. Okay, using the right hand rule, if you're twisting your fingers in the direction of rotation, your thumb will be sticking out to the negative J direction. So we know that it's the negative J direction there. So how did we get this? Right hand rule. Okay. Since this is a video, I'm going to go through this quickly because you can pause it if you need more help with it. Okay. Next thing we're going to talk about here is equivalent systems. So this is a really important concept that we're going to be kind of going over throughout the rest of this class as well. I think I've pretty much said that about every topic, but it's true. So basically, we can take a system that has a bunch of forces, couples, moments, everything acting on it, and we can replace it by something called an equivalent system with just one single resultant force acting at a specific point and one resultant couple moment instead of having to deal with all of these different forces on the system. So a system is equivalent if the external effects it produces on the body are the same caused by those of the original force and moment system. External effects can include translation, rotation, if a body is free to move, but in our case, most of our bodies are in static equilibrium, so these are going to be reaction forces. We'll talk a little bit more about reaction forces later. So here is an illustrative example, and I'm going to kind of walk you guys through this. So what I want you to do, I have a stick here, right? And I want you to consider holding the stick in the first figure that's subject to the force F at point A. Okay, now imagine attaching a pair of equal but opposite forces, F and negative F, at point B, just like you see right here. Okay, this is on the line of action of F, and we can see that negative F at B and F at A cancel each other out. So I'm going to uncircle this for a second. The negative F at B and the F at A cancel, and we get this. Okay, so leaving only basically the force at point B. Now the force F has been now moved from A to B, but we haven't modified the external effect on the stick, right? We started out with this system, and we now have this system, and we have the same external effect that's happening. Basically, the reaction at the grip remains the same. This demonstrates the principle of transmissibility, which states that a force acting in a body, or the stick, is a sliding vector since it can be applied at any point along the line of action. We can also use the above procedure to move a force to any point that is not on the line of action of a force. Okay, so if F is applied perpendicular to the stick, as in this figure here, then we can attach a pair of equal and opposite forces, so right here, F and negative F at B, and force F is now applied at B, and the two other forces, F at A and negative F at B, these form a couple that produce the couple moment M equals FD right here. Therefore, the force can be moved from A to B, provided a couple moment M is added to maintain an equivalent system. This couple moment is determined by taking the moment of F about B, and since M is actually a free vector, it can act at any point on the stick. In both cases, the systems are equivalent, which causes a downward force F and a clockwise couple moment M to be felt at that grip. So we're basically getting the exact same reaction, the external reaction, but we can replace these forces with equivalent systems. Okay, so now here are some figures that show a system of forces and couple moments and what we're trying to do here. So basically what we're saying is, similar to before, the resultant force is equal to the sum of all forces. The resultant moment is equal to the sum of all moments at M and all moments, at point O, including all moments acting on the system in general. And for 2D systems, if we consider the XY plane, then this is the scalar formulation of that. And I'm going to show you an example in the 2D system and as well in the 3D system after that. Okay, so this is a very similar problem to what we had before, but now we want to replace all the forces and couple systems shown by an equivalent resultant force and couple moment acting at point O. So we're going to start here with the force summation. And basically we have the resultant force in the x direction would be equal to the sum of all forces in the x direction. So we would have FR in the x direction is equal to, I'm going to put all of these into x direction forces, and y direction, okay, now we can sum. We have 3 cosine 30 plus 3 over 5 times 5, and we get 5.598 kilonewtons going to the right because it's positive. we're saying right is positive. We're saying up is positive here. And the y is equal to the sum of all forces in the y direction. And here we just basically have the 3 sine 30 minus 5 times 4 over 5 minus 4, and we end up getting negative, so 6.50 kilonewton in the downward direction. And from Pythagorean theorem, I can say that the resultant force is equal to the sum of FRX squared plus FR in the y squared, and I get 5.598 squared plus 6.50 squared, and my final answer there and that is the resultant force. If I want to know which direction it acts in, theta is equal to tangent inverse of F resultant in the y divided by F resultant in the x, and I get 49.3 degrees. Okay, now for the moment summation, I'm going to draw the equivalent system for you as well, but I just want to show you the math first. For the moment summation here, we have sum of resultant moment about 0.0, we'll say counterclockwise is positive. That's just equal to the sum of all moments on the system. So our MRO is equal to our 3 sine 30 times a moment arm of 0.2 minus 3 cosine 30 times a moment arm of 0.1 plus 3 over 5 times 5 times 0.1 minus 4 over 5 times 5 times 0.5 minus 4 times 0.2. I know I went through that pretty quickly, but we've gone over a couple of moment summations before. So I want to make sure you guys take a second, stop this. If that didn't make sense, make sure that you can go through this process and understand where all of those moment arms came from. Basically, it's 2.46 kilonewton meters in the clockwise direction. And now if I want to draw the equivalent system, this is my point O. I have my resultant in the X, my resultant in the Y. I have my total resultant, and I have the moment about 0.0, and we know it's in the clockwise direction. That would be my MRO. And this here is my total of what I've been trying to solve for. Okay. Let's continue and try another example, but we'll take it now to a 3D system. Okay. So the structural member here is subject to a couple moment M and the forces F1 and F2. And our goal is to replace this system by an equivalent resultant force and couple moment that acts at the base or point O right here, which is defined as the origin of the system. Okay. So we're going to go ahead and do vector analysis here because it's a 3D system and it can be kind of simplified using Cartesian vectors. So the first thing I want to do is I want to be able to put the forces into Cartesian vectors. So I have F1, it's acting, where is my F1 force? Directly down along the z-axis. So I can really easily write that as negative 800 in the K. For F2, I need to figure out what direction F2 is acting in here. So the best thing for me to do is take the magnitude and multiply it by RCB divided by the magnitude of RCB because I want to get that unit vector and figure out what direction it's acting in. So to get from C to B, I need to go 0.15 in the I plus 0.1 in the J divided by the square root of 0.15 squared plus 0.1 squared. And I end up getting F2 is equal to negative 249.6 in the I plus 166.4 in the J. And that's in newtons. Okay. And the moment here is equal to, now I have the 500. So this here, I have different components of that 500 and they act in different directions. So I'm going to take the 500 Newton meter. I'm going to split it up into components here and rotational components there. So here, the J direction, this, I should maybe put this in a different color, put it in pink. This direction here is going to produce a negative rotation if I'm assuming counterclockwise is positive. So I'm going to say that that component is negative 500 times the 4/5 component of that 3, 4, 5 triangle. That's in the J direction. But then I'm going to add the 500 because it's going up in the K direction. Okay, and I can simplify this by saying it's negative 400 in the J plus 300 in the K, and that's all in Newton meters. Okay, now for the force summation, I have the resultant force is equal to the sum of forces, which is just basically F1 plus F2. If I add those together, I have 800 in the K minus 249.6 in the I plus the 166.4 in the J. And if I add all that up, I get negative 250 in the I plus 166 in the J minus 800 in the K. And that's all in newtons. And now I can do the moment summation here. So I have my M resultant about 0.0 is equal to the sum of all moments plus the sum of any moments about 0.0 already. And so this is equal to the moments plus RC cross F1 plus RB cross F2, and those are all the forces and moments that I have on the system. So now I just have to plug everything in. I know the moment is negative 400J plus 300K, and then I have plus my 1K, because it directly acts in the K, times negative 800, and then plus this one I'll need to do the determinant for, because I have it in all three directions. Negative 0.15, 0.1, and 0, negative 249.6, 166.4, and 0. And when I simplify all of this out and add all like terms, or before I add all like terms, let me show you the simplification of all of this. I get 400 in the J plus the 300 in the K plus 0 plus, because K times K, remember, those go to 0, plus negative 166.4 in the I minus 249.6 in the J. And my total answer here, negative 166. Just do this in the I, minus 650 in the J, plus 300 in the K in Newton meters. And what I'm basically saying is the final system looks something like this. So I have my resultant force, and then I have my resultant moment that acts about, well, not the parallel axis. Let's try to draw this a little better. The resultant. So basically, these effects produce the same external effects, this is my answer here, as the first forces that were acting on the system here. We've just moved them to a different point. Okay. All right, a couple more examples to go for this topic. So let's go ahead and do example 13. Again, we want to replace the force and couple moment system acting on the beam by an equivalent resultant force and find where its line of action intersects the beam measured from point O. So the first thing I'm going to do, it's pretty straightforward to find our resultant moment. So here, oh, sorry, our resultant force. So here, let's first put all of our forces. We have 8 times 3 over 5, and we have 8 times 4 over 5. Okay, so our resultant here, we're going to have our Fx forces, which are the 8 times 3 over 5. We have the Fy forces, which are going to be negative 4 plus 8 times 4 over 5. Okay, here we get 4.8, 2.4. So square root of 4.8 squared plus 2.4 squared, we get 5.37. And theta, of course, where that resultant acts, is inverse tangent of 2.4 divided by 4.8. Okay. And now we have our moment summation. So we have sum of our moment resultant around O is just equal to sum of all the moments about point O. So this is where we want to figure out this part. Where the line of action intersects the beam measured from point O? The reason I'm doing the moment summation is because that is what will tell me, let me draw the figure first, where that line of action acts. So that was not a straight line. So this is my beam here, simply supported beam. And basically now I know that my resultant acts somewhere at an angle of theta. But what I want to know now is, where does this resultant act at what point along the beam measured from point O? What is this? What's the distance? So to find that, I can use the moment summation because this gives me some information about distance. So I can say that, well, FR is equal to 2.4 in the y direction. So in this direction, I have 2.4. This direction, I have 4.8. Let me sum all the moments now. I would have 2.4 times d. I'm going to sum them all around point O right here. Okay, that's the resultant. But that has to be equal to all of the moment summation of this guy. So what's the moment summation of this now? Well, that's going to be the negative 4 times the moment arm of 1.5 minus the 15 minus the 8 times 3 over 5 times 0.5 plus the 8 times 4 over 5 times 4.5, and I end up getting D is 2.25 meters. Okay, so basically what I'm saying is this is 2.25 meters from here to here. That's where my resultant acts. Okay. All right, so the last concept that we're going to go over before we call this topic quits, right, is distributed loading. So this is a super important concept about that comes up in kind of every type of structural system that you're going to design. So remember, we have point loads, and the definition of a point load is exactly what it sounds like. It is a load that is applied at one point. So for example, if I have a beam and I'm applying a point load or a load right here, that's just one point. This is a point load. Okay, but let's say I have a load like wind, okay, that acts along an entire length of an element like this, okay? Or let's say I have weight of a long member, right? This is a long member, and I have weight that acts kind of at every point. It's distributed. We call this a distributed load, okay? So for example, think of the wind, right? Think of the weight. And in a 3D system, you can think of the intensity of the distributed load almost like a pressure at each point on the surface. Okay, so the units of a distributed load in a 2D system would be pounds per foot or newtons per meter because it is distributed across length. It's a load distributed across a length. Okay. And most commonly in engineering, we consider loading along a single axis. So a lot of the problems that we'll be doing are going to be 2D systems. That's primarily going to be the type of systems that we deal with. So here I have a picture, although this is 3D, just to give you an image of what's going on. We would basically multiply px, this distance here, by the width of the beam, B, to obtain the distributed load W of x in units of pounds per foot. May have lost juice in here again. Okay, so let's talk again. We're going to multiply the P of x by the width of the beam to obtain the distributed load W of x, which is just going to look like this here, and that is going to be in units of force divided by length. Okay, now we can replace a coplanar parallel force system with a single equivalent resultant force acting at a specific location on the beam. So what does that mean? It means we can take this entire distributed loading and we can put it on a beam as just one force instead of having to draw it this way. But how do we do that? Okay, what is the magnitude of the resultant force? So if we have an infinite number of all of these parallel forces that act on the beam, all we have to do is sum all of them up. And what does it mean when we sum up an infinite number of forces? It means that we need to take an integral. Okay, so if dF acts along the element of some length dx and W of x is the force per unit length, then we can get the magnitude by just taking the area under the loading curve here. And then we come up with this formulation here, the integral, which is equal to the area under the curve. Okay, now the next question is, if we know the resultant, how do we figure out where the resultant acts? This x bar, we call it. To find that, all we need to do is figure out the geometric centroid of the area under the distributed load. And we can also do that because we know the line of action of the force passes through the centroid. So this is our formulation for determining the geometric centroid. We typically have really simple loading, so triangles or rectangles. So those are actually really easy to find, and I'll show you exactly how to do that. These become very straightforward. We'll do a couple of problems that are a little more difficult, and then we're going to do some that are much more common and straightforward to do. Okay. All right, so let's go ahead and try example 14. Before I get started here, I want to show you guys that this is more of an example to learn about how to solve these problems. However, typically in civil engineering design and structures, or when we're dealing with systems, this is more for civil, not for mechanical, but we typically won't see distributed loads that look like this. The types of distributed loads we really see and work with most often are more triangular like this because they correspond to self-weight of a member, or weight in general, or a lot of times triangular distributed that looks something like this. And so we won't have to really deal with these kinds of complex functions, but it's good to know how to deal with them just so we understand the theory behind this. Okay, but as you move forward, depending on the classes, you'll see more distributed loads that look like this and kind of less that look like this. Okay, so with that being said, let's go ahead and figure out what the magnitude and location of the equivalent resultant force acting on this shaft is. So to do that, we're going to say that the area, dA, this differential area, is equal to W, the magnitude of my resultant load, or the distributed load, times dx, that little width that I'm isolating here, dx. And this is equal to the function, which is 60x squared. And then dx, right? This is W. And this is my little isolated element dx. So now I know that the sum of all my forces, this has to be equal to the resultant. And actually, I'm going to assume that down is positive because my distributed loads are typically pushing down on elements because they're due to gravity. So here, my resultant force is equal to the integral over the area of dA, which is equal to the integral from 0 to 2 of 60x squared dx. And I can really easily solve for this integral. It's just 60 times x cubed divided by 3 from 0 to 2. And then if I plug in the 0 and the 2, I get 2 cubed over 3 minus 0, and I'm left with 160. Okay, and if I want to know where that load acts, I just plug it into my formula for the geometric centroid, which is the integral of the area of x dA divided by the integral over the area of just dA. And I would get integral of 0 to 2 of x now times the function. This is like the force times the moment arm divided by the 160 that I just solved for. And I end up getting 60 times x to the 4th over 4 integrated from 0 to 2 divided by 160. And I can solve for my x bar as 1.5 meters. And that's pretty much it. Okay, we're going to go ahead and do the last example here. This is a little bit more typical of civil engineering structures. So what I'm going to start doing, this is a trapezoidal load. Okay, and we want to know the magnitude and location just like before, but I'm going to, instead of using those formulas and integrals, I'm going to split this up and just use geometry. So as you guys can see, this top triangle here, or I should say this top part, is just a triangle. And the bottom part is just a rectangle. So the first thing I'm going to do, I know that I have some resultant force, F1, acting somewhere along the geometric centroid, and I have some resultant force, F2, and that acts along the geometric centroid of that area 2. So this is going to be my area 2, the purple. Okay, and I know that this first one has to be from here to here is the 50. And then I know from here to the top is my other 50 because it tells me it goes to 100. So I'm just basically breaking this up into really easy to solve for shapes. And what I want to know is, what is this distance that I'll call x1? And what is this distance that I'm going to call x2? Okay, so my F1, my force 1, whenever I have a triangular distributed load or any distributed load, it's just the area under the curve. Well, what's the area of a rectangle? 1/2 times the height, which is 50, times the length, which is 9. So that resultant is 225. Well, what's the area of a rectangle now to get F2? It's just the base, 9, times the height of 50, which is 450 pounds. That's pretty much it. How do I get the geometric centroid of a triangle? I'm sorry, the geometric center. It acts a third away from the highest point. So this length here, x1, has to be 1/3 of 9. That's always going to be my geometric center for a triangle. And the geometric center for a rectangle is exactly half. Okay. Now, if I want to reduce all of this to a single resultant, how do I do that? Well, I'll say that my force resultant, I'm going to assume down as positive, is just equal to sum of F. My FR is equal to the 225 plus the 450, which is equal to 675 pounds. And that's my answer. Those are my, I just have to add these two. That's it. And if I want to know the location of the total resultant now, I can always sum moments. So the sum of the moments about point A, counterclockwise is positive, is equal to sum of all moments about A. I have the 675 times the final resultant is equal to the 225 times 3 plus 450 times 4.5. And I get my x bar is equal to 4 feet. Okay, and that is the end of this topic.